Oh, wow. Thank you so much. How are you today? Okay, so thank you for coming. It's amazing how many people are here today. I'm very excited to talk to you in the Science Cafe. I was just telling Sarah that I think I was the first speaker ever in season 1. So I'm happy to come back. This is like Survivor, you know, they re-invite you. So I'm one of those survivor back into the season 8. So the title of the presentation is Electrons for Sustainable Manufacturing. And so it's kind of like I want to start a little bit by discussing a little bit what those terms are. So I'm going to have the aid of the PowerPoint slides, as well as some toys, because what is an engineer without toys, after all, right? Nothing. We have to have toys. And also, some of my undergraduate students who are doing projects with me are going to have an opportunity to tell you what they're doing. So they're going to take the stand as well. So this is a little bit of the outline of my presentation. As I said, I'm going to start with some basic concepts, but I'm also going to be posting some questions to the audience because I'm going to need your help to figure this out. We're going to do it together, okay? Now, notice this temperature here. It's kind of like a thermometer, okay? So before I move forward, I want to tell you what this means. This is technology readiness level, okay? So it's like a thermometer that tells you how innovation and technology keeps progressing as you develop it, okay? So when you just start with an idea, oops, I just got an idea. You are at TRL level 1, okay? When you actually kind of conceptualize that idea and do some calculations, you are in TRL level 2. And then when you start doing some experimentation, you are at TRL level 3. So why this is important? Because this is what industry considers for adapting technology. The higher you are in the thermometer level, the closer you are to commercialization. And why I'm pointing this out? Because you're going to see this thermometer in several slides, okay? So the maximum level is TRL level 9. That's when you get ready doing all your testing in a real site. It doesn't mean it's commercial yet, but you have proved everything in a real site, and you have estimate costs and everything. So you're just looking for the financial funding to take it to the market, basically, if you take technology at that level. So let's start by that. So the first thing is manufacturing. What do we think when we say the word manufacturing? Okay, I already revealed it here. Most people typically think about making cars, right? Making airplanes. What else can you think of about manufacturing? Yes? Appliances, okay. Making devices, right, like cell phones and things like that. But and in a chemical engineering world, okay, manufacturing for us means making chemicals, okay? So basically, we're talking about transforming a raw material into a different material using a chemical process. So this picture is basically a picture of a facility where I started my life as a chemical engineer before I did my PhD and before I became a professor. So I was actually working in the chemical industry manufacturing chemicals. So for chemical engineers, manufacturing means making chemicals, okay? So why is that related? Well, because here we're seeing an airplane, and typically in an airplane, when we think about manufacturing, they're putting components together, same thing in a car. But if we take a closer look at that airplane here, a Boeing or a Bus or whatever type of airplane, there are different components, for instance, that I'm going to highlight. One component here is the material that the airplane is made of. It's aluminum alloys. Why? Because it's light, it's corrosion resistant, and it's an alloy. That means it's not pure aluminum, okay? Now, where did that aluminum came from? You can see you also use some of that aluminum for cooking your turkey during Thanksgiving, right? Or we use it every day as a pan in appliances, etc. That aluminum came from aluminum. In this case, these are aluminum bars, okay? So it's different. In here is formed as an alloy. In here is more like aluminum, more pure like the metal. There is going to be some contaminants because we cannot prevent that, but it's not being alloyed with other materials purposely. But where this aluminum came from? We have to go back. So look at this. Even though we're talking about an airplane, we're following the chain of where this material came from. Came from something that is called alumina, which is La2O3. I'm going to minimize the chemical reactions, but I had to point that out. Okay? So, wow, why is this so exciting to me? Because to go from here to here, and my students know what I'm going to say, we use an electrochemical process. Okay? It's the whole Herol process. And I have to say this. If you didn't know this, before this process was invented to go from here to here, aluminum was as expensive as silver, which means today's price, whoever has a computer can check it in the market, $250 per pound, silver. Aluminum, 85 cents per pound. Only possible, because the whole Herol process, which is an electrochemical process, but don't tell anybody yet, because I haven't got it yet. So that's what happened there. But before that, that came from bauxite, ore, which has a lot more materials on it, so therefore it needs to be processed to convert these and go into that. So what we're looking at that even though we're making airplanes, manufacturing airplanes, there is a chemical engineering route to start getting there, okay? That brings me about the chemical industry. So here is a map that has a little bit of the distribution of the chemical industry in the United States from 1996 to 2005. I should kind of update this graph about the location, and here you can see the states. But what do? As I said, they transform raw materials into other materials. The majority of these materials are chemicals, and there are over 100,000 chemicals produced by the chemical industry. And the chemical industry could be classified into commodity chemicals. That means they're made at large scale, and they have to be very inexpensive because they make so much of it that they sell and they make their value by bulk, okay? Examples of that are ethylene, ammonia, etc. And then the specialty chemicals are made in very small quantities, and they're special. They are more expensive because they had a higher value. And for examples of that will be biomedical drugs, okay? So other chemicals that are used a very small quantity, but that they are required to make specialized materials. So we have the two spectrum. These processes are continuous, designed to never stop, typically, and these processes are batch, okay? And we'll see why that will be important later. So that's chemical manufacturing for us, chemical engineers. Now, how does chemical transformation of raw materials take place? We talk about manufacturing. Remember, it was in the title. So what do you think the next relationship is with the title? Electrons, yes, thank you. So this transformation of raw materials takes place because it's a combination of atoms to form molecules or a decomposition of the molecule to lead to atoms, okay? So those chemical reactions typically take place in this type of reactors, which is actually much bigger than me, except that I couldn't bring the scale of the picture to my height, but anything is higher or taller than me. So, so in a chemical reaction, generally you could say, oh, A goes to B. Here is a chemical reaction in which we have methane being combusted, right? And it produces CO2 and water. Why is this a good reaction? Well, because it's an exothermic reaction, it produces heat, and it's basically what we use to burn to produce heat. Why? Because these chemical reactors need to be majority heated to reach the temperature of the reaction. Not necessarily because all the reactions are endothermic, but because of kinetics limitations, okay? So why is that important? Keep in mind, I need to burn a fuel to heat this reactor so that my reaction can take place. An example of that reaction, ammonia synthesis. I take hydrogen and nitrogen and I make it ammonia. Why did I choose this example? Because for those who are taking chemistry, it's an exothermic reaction. However, I need to operate at 400 to 500 degrees Celsius for that reaction to take place. Why? Because of kinetics limitation. So the only way I can do it in the reactor, I have to heat it. So how that reactor looks like inside, you have a shell, and a steam is probably heating your reactor, and you have to control temperature. Have you ever started the heater in your house? All the time. I bet I hope you have it on today. Okay, how long does it take for your house to reach that temperature? Some time, right? Mine takes a long time. That's what I never showed you. That's why my bill is so big, anyways. But it doesn't happen instantaneously. The larger the room, the harder to heat. The larger the reactor, the larger to heat. So you have to give it a time for it to work. So keep all this in mind, please. Remember this point because we'll come back to that. But are there other ways to drive chemical change? Yes. So this is, for instance, a picture of, here is hydrogen, oxygen atoms, and then here we have water. So what this picture is really showing here is, what you see here are the electrons, right, in the last orbital, which is basically when atoms react, is because they want to share that with other atoms to become more stable. That's the case of our friend hydrogens with oxygen that combine and produce water. So if you think about the atoms as being planets and the electrons as being satellites, you have to bring the planets away so that the satellites can separate when you want to break water to the original atoms. Oops, sorry. Too excited. But what's the key here? For combining, what do we need to do? Controlling these electrons. If I could directly touch the electrons, I wouldn't need heat. That's the beauty about it. We can control the electrons, we don't need heat. And then I'll prove you how. Through electrochemical processes. That's what I do for a living. So an electrochemical process is an electrochemical cell, has two compartments, an anode and a cathode. And then even though you're seeing it as A goes to an ion and oxidizes, releasing electrons, and then B is reduced, at the end of the day, when you add A plus B, you have the material that you were looking for. The difference is, I'm basically, through an electric circuit, directly applying or removing electrons out of the system to drive the electrochemical reaction. So what do you think is more efficient? To heat so that the electrons shake and they can combine, or to directly touch them and say, move? What do you think is more efficient? The second one, right? So that's what we do. Now, even though it sounds simple and all that, there are certain things that we work to make these systems work. So all of you probably have heard about electrochemical processes. If you have batteries, do you have batteries? Yes. Cell phones, all appliances, we cannot live without batteries. But that's the thing. Everybody knows about batteries. How many of you knew that aluminum is made today because of an electrochemical process? Hopefully my students raise their hand. Okay, so now you know it, right? So every time you cook, remember about electrochemistry. So why are electrochemical processes nice? Why are we interested in them? They're very simple to control, on, off. So we control the voltage or we control the current. We don't have to typically heat to the temperature and wait for the temperature to take place. We don't have to separate, but I'm not going to go into many details. Typically, the beauty of electrochemistry is to operate at mild temperatures. There is high temperature electrochemistry, but my passion has always been in the belief of low temperature because that's what electrochemistry enables. And then there are other advantages as well. One of them is the integration with renewable energy. What happened today, we have solar panels, we have wind turbines, right? So if we can pull directly electrons from them, we can make a chemical without burning a fuel, which is the difference in the traditional chemical reactor. And they are modular. How do I prove you they're modular? Those are some pictures. This is a little one that I'm going to tell you later what it does, okay? Not yet. I will tell you in a few minutes what this cell will do very soon. So how are electrochemical processes related to sustainable manufacturing? Sustainable manufacturing is basically if we're going to create materials, processes, chemicals, we need to not only think about a substantial financial profit, but we also have to think about a substantial good environmental impact, okay? Which is a different mind change compared to several years ago. So most companies have sustainability goals. So let's revisit my list and see if from this list, I'm going to put a star in what is related to sustainable manufacturing. I will minimize operation costs. I will operate at low temperatures and low pressure, so it's more environmental friendly. I will increase the selectivity of the products because directly I'm moving electrons and not heating everything in a cooking pot, okay? You're just treating them individually, the ingredients of your recipe, okay? You reduce the number of reaction steps. You are producing less pollutants or chemicals, and super important today, we can couple with renewable energy, which the other process cannot do, the classical chemical engineering process. And finally, they are modular. But why modular is important? Modular is important because when we think about making a chemical, we also have to think that there is a transportation issue of bringing that chemical to the site where it's going to be used. And if you are transporting that chemical, then it has transportation costs. And what else is going to have? It's going to have to be carried somewhere, right? So it's producing CO2 emissions and other things. So because it's modular, it could be made on the site. So that's what I love them so much. You notice I love this thing? Okay. So what chemicals or materials are manufactured electrochemically? Can you answer that question? Aluminum. What else? Chlorine. Okay. So chlorine, here is a cartoon of that, what we can make with chlorine. PVC pipes, we couldn't drink. Clean water, we couldn't have acetaminophen without chlorine because these are all medicines that have chlorine. As a matter of fact, chlorine industry is one of the largest industry in the chemical industry, and the only way to make it is electrochemically, okay? All we use is salt, sodium chloride, and it's separated into chlorine. And there is another chemical that is made in this process, which is sodium hydroxide, which is also used for many other chemicals and manufacturing of different things, including soaps. So what is important? Well, even though chlorine, we don't think about it that much, we couldn't have clean water without it. You couldn't have pain medication. You couldn't have this type of plastics. They wouldn't exist, okay? So that's what is important. So it advances many other processes. The other big example is the adiponitrile process. The adiponitrile process is adiponitrile is the monomer to make nylon, okay? And nylon has many applications. But however, why can we only cite 3? Everything else people think about batteries, fuel cells, plating, all those are electrochemical processes, but not that many in the chemical industry. So this is what's happening. And this is based on studies that I have done, not only by myself, but other researchers as well, and surveys that we had done at the center as well, is there are some preconceptions within the chemical engineering audience, okay? One of them, there is a lack in education. Not many people know about electrochemistry and electrochemical technologies, okay? They think that making these cells is difficult. They don't know how to make it. They believe capital costs are high, and then they think that the electrolysis processes consume lots of energy. So one of the things that we're doing at the center is basically educating people to explain to them what things have changed and why these preconceptions shouldn't be there anymore. The one that we need to work very hard is in educating people to let them know what has changed. And so if we look at an outlook, what has changed? Things that we can do today. Today we have nanotechnology so that we can make more efficient materials that we couldn't do before. Today, we have advanced modeling to a level that we can make little molecules on the screen in a computer, synthesize them, and then couple those models into an electrochemical process so that we can design the reactors. These things that the industry believe is difficult to do because they are not used to that, because chemical engineers are not used to this. They are used to the big things that I showed you before. And then we can do in situ characterization, so we can actually watch very little inside and know what's happening. When you put all this together, we have advanced in so many other technologies that is an untapped field that we have there that we haven't touched, in which we can make improvement for sustainable manufacturing. Okay? And I'm going to prove you that with 3 examples. Okay? Before my student talks, how we're doing in time. Okay. So the first one is graphene manufacturing. Why did I choose this? Because this we're making a material. And we're making a material using electrochemical technology. But the beauty about it is that we're using coal, yes, C-O-A-L, coal, to make graphene. So why they are different? Well, they have carbon, but they're different. So graphene is a super material. It's very thin, transparent, conductive, light, maximum 1 layer, 1 nanometer. And coal is very different. It's a heterogeneous material. It's kind of like a fruit cake, okay? Very diverse. So what we're doing is, there are challenges with this super material that have been discovered recently within the last decade. Is the challenges have to do with scalability, production cost, and purity. So what we're doing is working in these 3 issues simultaneously. So we're working in making it scalable, reducing the production cost, and the purity. And how we're doing it? We're doing it with an electrochemical process, in which I'm going to start using my toys here. We basically take the coal as it comes from the state of Ohio, okay, which is here. We pass it through an electrolysis process, which I didn't bring the cell today, and it produces this material that I have here, which is called an electrolyzed char, or an electrolyzed coal. So notice that in that process, I'm also producing hydrogen. I'm happy making hydrogen, because then I'm going to use it for the synthesis of graphene, as well as my electrolyzed coal. So what happened? When I apply electricity to the coal, in the presence of water, I'm modifying the surface of the coal particles, enabling the conversion of new structures at the surface that lead to the synthesis of graphene. That's what electrochemistry is doing for us today. So, going back to my table there. So what we want to do? We want to do it less expensive. Why? We're using coal, which is very inexpensive, and we need very little coal to make a lot of graphene, because graphene is a very thin material. And if you want to see it later, we have here an example of graphene that we're making at the center using Ohio coal, okay? So you could see here that our graphene was made with Ohio coal. So what we're doing here is going to be a modular process, and one of the things that we're doing in the technology is that we're basically transferring the graphene, okay, without the use of other more expensive materials because of the help of electrochemistry. And here is an example of our graphene, which grows in copper, now being transferred in another material without the use of expensive chemicals. So what's the beauty about it? It's a modular process. I can bring to the manufacturing side who wants to use graphene, and it could be made and transferred and put in the thing where you need it to be used, okay? So, value proposition. My thermometer here. We're using, what are the advantages? We're using a raw material that is secure. We're recycling everything. We're eliminating the support to transfer the graphene. We have flexibility for any application. We are at TRL level 4. And what we're looking is scaling up. So that's why we're at TRL level 4, because we are at a smaller scale. And what we're working right now is in demonstrated that we can make the same graphene at this larger size so that we can go into TRL level 6. Simultaneously with this technology, we're in close collaboration with the industry and end users, so we're learning from them what are the applications and working with them on transferring the graphene to their applications. So in this thermometer, we're here. Hopefully, we'll get there very soon. Okay? The other technology. One of my favorites. I mean, all of them are, but it's just ammonia. I love ammonia. I'm crazy, right? So ammonia is one of my favorite chemicals in the world, and I had the privilege that my first job was in an ammonia plant. So it's amazing. So ammonia, people don't know, but it's used for many applications, including the fertilizer industry, okay? And here are some products in which they can be used. Plastics, yes, unfortunately, it can be used for explosive as well, but it has a lot more applications. And you could see the ammonia production over the world, etc. Ammonia is the example of heterogeneous catalysis for a chemical engineer. The process to make ammonia is called the Haber-Bosch process. So for a chemical engineer, to work in an ammonia process for the first time in their life is like paradise, you know, like Disneyland. Okay, no advertising, but you feel like Disneyland in an ammonia plant. Okay, so despite the importance of ammonia, it has major sustainability issues, and I'm going to tell you what they are. The first thing is, unfortunately, it produces a lot of carbon dioxide emissions because of the way it is made, but we cannot live without it. We couldn't eat corn today the way we eat corn without ammonia, okay? With the population growth, we're going to need more food, so we need to make this one of the most perfect nitrogen fertilizers, okay? I say one of the most perfect because of the CO2 emissions. If we don't have the CO2 emissions, it will be perfect, okay? So, and notice the temperature, the synthesis, 400 to 500 degrees Celsius, is high temperature and high pressure. So it requires a very expensive vessel, etc. But ammonia is a commodity chemical. That means in large quantities, it's cheap because the process is designed to be cheap at large quantities. If you want to make small quantities, it's very expensive because it's reversed in scalability and cost. Why do I bring that up? That's why ammonia has to be made in certain areas and transported. If we could make it on the site, we didn't need to transport it. So the Haber-Bosch process, what I was saying, is favorable at the scale. So can electrochemistry can do a better process that is modular, efficient, and economically favorable, where we could couple renewable energy with water, nitrogen from air, and basically produce ammonia. That's what we're doing. How we're doing it? Well, we have a technology in which we're able to control the species at the surface of the catalyst. And that happens, so this is an electrochemical cell, and there are two reactions taking place, and one reaction leads to the synthesis of ammonia. And here is an example of our profile. So for every cell, we're basically right now pulling about 500 millivolts to 250 millivolts. So it's a very low voltage process because if you remember, a AA battery is 1.5 volts. So I'm talking about half of a volt, okay? So why is this important? Well, because making ammonia at 25 degrees Celsius was something that people thought it was impossible, okay? So this is a tremendous advance in technology. And it's basically because we have better materials and better way to control the surface of the catalyst, what's present on it. So what's my view? And I'm going to look at my friend Sarah over there because we're trying to make this work together. So what I like to do is that this little cell that I have here, okay, which is my ammonia cell, can help us grow a garden. So, but what will happen is this is a garden of approximately 100 feet square per person, but then we will have to think about different ways because now we will have the advantage to administer ammonia directly and more effectively on the plant. And she's the plant biologist and the crazy electrochemistry. So that's what I work with her on this, okay? Now, but what we also like to do is scaling it up. And how do we scale it up? We'll take several of those cells and we could put it now an application for the farm. Okay? So here is my thermometer, where we are. Literally, I really started hearing this crazy idea. I can do this, and I'm going to do it like that. You know, and from what you read, people said it was impossible to do nitrogen recombination at this temperature. So today we're at TRL level 3. Why? Because we had some demonstrations in the system. We can make ammonia, but we need to still work more in the catalysis and in the optimization. But not only that, we want to be transformational, which means I need Sarah to help me understand how that's going to work on the plants, because now it is possible that with this way to administer fertilizers, the consumption of ammonia actually decreases, because these estimated numbers that I shared with you, we're not using ammonia directly. It was using ammonia's friends, like ammonia sulfate or ammonia or urea, etc. Does that make sense? Yeah? I don't see. Okay. And finally, the last one that I want to show is actually the father of the ammonia synthesis. For years, I was doing a process that is called ammonia electrolysis, in which I was breaking down ammonia, NH3, into nitrogen and hydrogen. So the ammonia synthesis is the reverse of that. Okay? So where do we use it? One of the low-hanging fruit applications is for wastewater treatment. You could see here, this is a problem that we actually were affected in the state of Ohio very recently, and it's called Algae Bloom. Why is it caused? 2 reasons. First, before algae becomes algae, they are spores. Right, Sarah? My biology is right. So these spores are fed with ammonia, not with nitrates. Okay, so initially you had ammonia in the area, your spores become algae. Once they're grown into algae, then they eat nitrates. So the more nitrates, they grow. So what happened was, when the wastewater treatment plants were designed, they were designed only to remove ammonia, but to discharge nitrates. They didn't think nitrates was a problem. The challenge today is, if you want to convert every wastewater treatment that discharges nitrates and eliminate that, it will be a tremendous investment, which is crazy with today's technology, except, of course, if you use the green box, which will make it much cheaper. So how does it work in the green box? You have ammonia-contaminated water, produce clean water, nitrogen, and hydrogen. And what I want to show last is how this was integrated at the Athens wastewater treatment plant. So if you're driven around, you've seen a little trailer hanging there. That's this technology. So in a partnership with the Athens wastewater treatment plant, they've been great. Here is a little bit history about the Athens wastewater treatment plant. Unfortunately, the way this plant were created, nitrates is part of not what is being looked at right now, but things will change. So they did some renovations recently, which was about $18 million, and this is what they changed. These renovations in the Athens wastewater treatment plant took place in a period of 2 years and included like site construction, May 2015, etc. So it basically took them 2 years, and you could see excavation, tanks, crazy stuff, very heavy duty. A lot of cement is used, right, etc. Then we build a unit that is the green box, in which we couple some chemical engineering off-the-shelf equipment that already exists, pumps, with the ammonia green box. And we put it in the Athens wastewater treatment plant, and the construction started in June of 2015. So in June of 2015, we started assembling and putting regenerant tanks and ammonia electrolyzer and put everything in a trailer. And this actually took basically 2 months. And the Athens wastewater treatment plant took 2 years to renovate. So we basically put everything in a trailer and just plug it in as a washer machine for the Athens wastewater treatment plant. And then since then, we did some testing, and we're revitalizing more the testing. So we were able to see here is real data from the Athens wastewater treatment plant, ammonia concentration, 0 ammonia coming out of our system. And then we treat that ammonia in the green box that is behind there, and we were removing ammonia about 10.5 milligrams per minute But that happened in a single cell like this. So I have 5 of these at the Athens wastewater treatment plant. So it's kind of an illustration of how we can actually make things modular and smaller, and how we can handle that many volumes of solution, and then being able to convert it into something that can be transported, etc. So, being said that, in thermometer, this is a TRL level 9. It's still being used, actually now by some of my colleagues at CER, which is a Construction Engineering Research Laboratory of the Department of Defense in a facility. And the economics is great, and we're seeking for partners for further evaluation, for instance, the EPA, commercialization, and potentially manufacturing. So, before I move forward, I'm almost done here, and I'd like to acknowledge the financial support of the people who have funded some of the research and development that you see here, including my grants from the Department of Defense, who helped advance tremendously the ammonia green box technology, as well as the Ohio Department of Development, which have been funded the work on graphene, an EASE award that helped me fund the work that I'm doing in sustainable manufacturing for the chemical industry, so that I can understand how we can help them, and also the Center for Electrochemical Engineering Research. So, key points that I want to make is electrochemical technologies can enable breakthrough. I hope you believe me on that. Do you believe me? All right. So, electrochemical process can contribute to economical and sustainable manufacturing. They are modular. I just showed you some toys over there. But we still need to work on this. And I need your help on the last one. We need to overcome the lack in education. And for that, we need partnerships between industry, university, government, public, are critical. I want to focus on that because my talk is about sustainability. But sustainability in education as well. I need the next me, or more of the next me. We're going to continue doing this. So what we're doing is also making what I call a sustainable electrochemical engineering education program to bring the next generation here to replace me, okay? So how do we do it? Through several things: course curricula, independent research and design projects, outreach programs, both through K through 12, industry, implemented through university and professional societies, curriculum development collaboration, also with the Patton College of Education to train the science teacher. Sorry, I get too excited that I need to breathe. I get too excited when I get to introduce the next generation, so my heart pumps so hard. So what I want to show is, I want them to tell you how independent study works for them, and I'm going to give Burt Niehaus the opportunity to talk about how he's doing this concept for his project, and he's going to take a few minutes, and then we can take questions. So Burt is coming here, and I think he's going to have to use this microphone, right?
This? Do I have a little clicker?
The clicker is here.
Oh, okay.
Yeah.
Cool, yeah.
Okay.
Well, hello. I'm Burt Niehaus. I'm a junior chemical engineer, and I work for Dr. Botte. And as hopefully you got from her presentation, you can kind of see the motivation for why we want to get involved and learn more and get involved in these electrochemical technologies. So I'm going to talk about a project we work on, which is the American Institute of Chemical Engineers ChemiCar competition. So our overall design, there's about 10 to 15 students, all chemical engineers, except for an energy engineer and mechanical engineer. Our objective is to design a car that has to travel a certain distance and stop. So we work with Dr. Botte to employ kind of electrochemical technologies and learn from her and design these sort of materials. So first, I just want to introduce our team. I think a couple people are in the audience from our team. Like I said, mostly junior chemical engineers, but we have everywhere from freshmen to seniors and energy engineers and mechanical engineer. So we're interdisciplinary, but mostly chemical engineers. And so our car is powered using the sustainable electrochemical processes that Dr. Botte has introduced. So this is our car right here, and inside this casing is our battery. So we use more or less a homemade commercial aluminum air battery. So you can see from the diagram, if you guys can follow, as the metal is oxidized and it brings in oxygen on the outside that's reduced, and it's a battery. So we have 6 cells, and this can turn our car on and off and power it to go a certain distance. But we also have to stop at a certain distance. So a unique thing about the electrochemical facet of our car is that it can start and stop on a dime using what we have here on the side is, maybe you can't see it, there's an Arduino hooked up. And how this whole thing works is we have a precipitation reaction. So you'll see, hopefully if this video, nope, maybe I have to get this video to play. Do you think you can?
See if I can help you.
Okay, so we mix sodium sulfate and calcium chloride, and as we stir the solution, it becomes cloudy, and okay, so we'll see it. And we have a laser passing through the solution, if you can see that. So we're basically measuring how long this reaction takes, and because we can't install a timer, that would make it too easy for us, so we have to time it using this chemical reaction, and then we can select a time and a point where, using the Arduino, we can cut the circuit and stop the car. So hopefully, and we might have to play it one more time.
Yeah, sure.
Sorry. So this is going to be this car right here, and you guys can see it running in my my crudely shot video. Then so it's going to go a long distance, about 15 meters, and then toward the end it's just going to stop right when we need it to. So that's the general operation of our car. Why we do it? It's a design competition, an opportunity for us to really get to learn more and apply our engineering skills. So we get to use state-of-the-art technologies like a commercial aluminum air battery. We get to learn about material synthesis, electrochemical technology, and it's really great working with Dr. Botte and her at the Center for Electrochemical Engineering Research. There's a lot of postdocs, graduate students who are great resources for us to learn more. And through doing this all, we learn basic electrochemistry. We learn how to use Arduinos and microcontrollers, and I mean the list goes on. Research skills, problem-solving skills. It's more than just classroom education. We actually get to do hands-on and learn by doing. That's you. Okay,
Yeah.
Thank you.
So thank you. So that you had an opportunity to hear from Burt. He will be around, and really don't now. You can see his little car, but this is a hot news. I actually added this at last minute in my slide. We are looking for 12 energetic undergraduate students who want to do research with us at the Center for Electrochemical Engineering Research through the PACE program, and you can either email directly the center or Dr. Muthavel, who is sitting over there, who is going to organize all the interviews and the process. That's how we get people like Burt and other people to work at the center and help transfer the lack in education that exists in electrochemical technologies. Thank you.
And no, you're not done yet. Questions? Time for the quiz, guys.
You're an engineer. You have to deal with practical matters.
Do we need the microphone for the question, for the video, or no?
You're going to repeat the question.
Oh, you didn't tell me that trick. Okay, so
You talk about the EPA and nitrates.
yes.
Under the current administration, nitrates are simply collateral damage and are not to be any further consideration. They're no constraint. How does that affect your project?
I have to repeat the question, right? So let me articulate it. So under the nitrates are a collateral and are not seen as a big problem today. Well, that's one of the things that had to do, unfortunately, with remediation technologies. It's going to be always an issue to confront. But I think what we're seeing today is becoming so obvious that people are going to have to look at it. I mean, it's not only in Ohio, it's also in Florida. In different rivers, in the sea, recently very near Naples. I was there last summer, and we had some problems there as well. I think one idea is the industry are looking at it for chemical processing of waste. So that might be the first area in which we'll actually create an impact while the regulations catch up. I wish I could control that part, But my job as an engineer is to demonstrate that it's much more cheaper than anything else, and it could make a solution for providing clean water. So hopefully, because of the decrease in cost and operational capital equipment infrastructure that exists today, it could be used in wastewater treatment plants. Because the next wastewater treatment plant is going to require to invest, right? So if I can demonstrate that by putting this is cheaper, then they have to do it. I don't know if that answers your question. I wish I had more influence, but all I have to do is educate, I guess, by preaching. Yes?
Did you say that in the sewage treatment case, you were breaking down the ammonia into nitrogen and hydrogen?
Yes, that's correct.
So, dumb question, but we want ammonia, we use a tremendous amount. It's not practical to separate it out, and there we go, ammonia.
Yes, that's a very, very, very good question. So the question he's asking is, in the wastewater treatment process today, we are breaking down the ammonia, which is NH3, into nitrogen and hydrogen. Why don't we use it as a fertilizer? So there are several things there. First, when it gets to the wastewater treatment plant, it's diluted, okay? So when you urinate, when you pee, if you could collect that, it will be a much higher concentration. But when it gets to the wastewater treatment plant, it goes through several processes of dilution. So recovering of that creates an economic challenge for the wastewater treatment plants. And the second challenge is, even though ammonia is a great chemical, if you're going to separate it, distribution of the chemical off-season becomes a challenge. So now your wastewater treatment facility will be an ammonia supplier, and they're not designed for that economic business. So what happens there is, when we have winter, where our wastewater treatment plant will store the ammonia, for instance. It will have to be shipped somewhere else to be used, and that creates an economic hurdle in the economics. So it's an economics as well as management. Yes?
In the manufacturing processes of electrochemical processes, is there any significant corrosion on the cathode and anode inside the reactor?
So his question is if in the electrochemical processes there's significant corrosion in the cathode or the anode. I think it will be specific to every particular process. What you do is, for instance, each of the chemistries that I show here are kind of different. The cold chemistry is acid, so the materials, we select materials that are tolerant to the media. The chemistry for ammonia synthesis is alkaline, so we select materials that are designed for that. So in terms of corrosion, if you choose the proper materials, it shouldn't be a challenge. What we're trying to do is the opposite to corrosion. Corrosion are electrochemical reactions that you want to stop. Here, I want the reactions to go really fast because I want to make the chemicals. Yes?
How dirty a process is it to change coal into graphene? How do you control that?
Yes, so that's a good question. She's asking, how is the process, because coal has many impurities, right? How can I control transforming the coal into graphene? So what we do is, in my little toys here, so the coal is grinded, the particle size that is typically grinded in a wastewater treatment plant. And what happens is when you do the electrolysis, we're basically touching the surface of the coal, and any other thing that comes out of the coal stays in the electrolyte. So it doesn't carry into the coal char here that is electrolyzed. So what happened now is, because we basically modify the surface of this coal, now we can heat the temperature of this coal a little bit and release gases, premium gases that were created because of the surface that I modify, and then I use that to synthesize the graphene. So if I don't do the electrolysis, I could not generate them. So basically, and keeping the impurities either within the coal or within the electrolyte that then I can recover. I'll give you an example. Coal have metals, mercury, and all those sort of things. What we have discovered is that we're removing it in the process, but where are we putting them? In the electrolyte. But that's not bad. If I put it in the electrolyte, how do you think they make rings? By plating. Now it's in my solution, and I can electroplate an ion of mercury and make it mercury or make it silver. So instead of going to air, I could connect it as a metal. So it is a really beautiful technology. But one thing that is important, if I use 1 ton of coal, I can produce a lot of graphene. The yield is very high because graphene is a single carbon atom, nano layer, very thin, and coal has a lot of carbon as well. So we're using electrochemical technology not only to make graphene, but also to potentially really clean the coal and get the metals out of the coal. And then you can actually sell the metals because there is silver, and even mercury has values, amalgam, etc. So, yes?
So you said when manufacturing chemicals through the process of using heat, the bigger the machine, the more heat you would have to use. When it comes to manufacturing chemicals through electrons, if you want to make a larger quantity, is there anything major that you would have to change in the process?
That's a very good question. So, wow. So, yeah, you should do research like that. Okay. So she's asking, when we have chemical process, we need a lot of heat because it's a large reactor. And when we're trying to scale up electrochemical reactors, what are the issues that are there? In the chemical reactors, the electrolysis, the reaction is done in the whole volume. Okay? And the job of chemical engineers is to optimize that. In the electrochemical process, the reaction is take place at the electrodes that you cannot see here. So when we scale this up, we need to make sure that we design so that the current can flow really fast through the electrode, because the current is what is going to touch each electron and say, wake up, it's time for you to react, right? So the largest issue there is what is called current distribution, to make sure that you design your system so that the current will flow really fast through the electrode. So that's why we do the modeling that I showed earlier, so that we can optimize what's the best size for each electrode. And then what you do is you stack. You know, instead of making a cell like this, I could make a larger cell like this, and I can put 10 of those together rather than making a big electrode like that. So it's an optimization process, but in that case, current is what you want to optimize through your system. Yes? Yes?
Why do you choose copper, which is also a metal, in the modular section?
Yes.
How will work the interaction? Again, back to the formula.
Yes, so that's a very good question. So she's asking in the process when I make graphene, why do I use copper? The thing what happen is the way to make graphene, you need to have a catalyst where the carbon can sit, okay? And copper is the perfect one to do that. Once you have, I take my coal, I electrolyze it, and then I apply a little heat, and I make some gas come out. That gas runs through my copper, and that's how I synthesize graphene. And we will use the hydrogen co-generated to help in the synthesis during the electrolysis. So what happens is copper is a material that is made electrochemically. So now, electrochemically, I can coat very thin copper and grow my graphene in there. I can dissolve my copper and recover it again, so I never use it. But to answer your question, the copper is the catalyst so that we can grow graphene. Yes?
Okay, last one.
Yeah, okay. Yes? To break down the ammonia into nitrogen is an endothermic reaction. Okay? To make ammonia is exothermic, which is the opposite. Okay, so her question is to break down the ammonia, NH3 to nitrogen and hydrogen was an endothermic reaction. It is an endothermic reaction. Oh, no, because the electrons is what is driving my reaction. So instead of applying heat, I'm basically applying the energy directly through the electrons. So I can operate at low temperature, 25 degrees Celsius, but the driving force is the potential, the current, the electrons directly. Otherwise, I will need a cracker at 600 degrees Celsius to break it down. Okay? Yes.
Okay, well, with that, I'd like to thank Dr. Botte.
Thank you.